So in a fit of inspiration, I actually wrote out all of today's notes ahead of time, and they're on the website. I'm very surprised with myself, but anyway. So we have it all. So we'll just. There will still be interactive elements, but I do have some stuff. So what I would like to talk about today is a kind of a move to the next step. So we've been talking about randomization and why it's an important primitive to get to know and become familiar with. I've given you some examples of how randomization gets used and where it can be effective for problems. I'm trying to argue that in some ways it can make things a lot simpler for the algorithm, while of course making the analysis a little bit harder. And to that extent, we actually spent some time just looking at analysis questions, like last lecture. How do you even analyze the behavior of a randomized algorithm, which is really the question of how do you analyze the behavior of a distribution? Because the description of the behavior of the algorithm is itself a distribution of some kind, a probability distribution. So that is one part of what I think of as sort of the two-headed monster of dealing with sort of modern algorithmic questions, especially things at scale, so randomization. And the other part of it, which is the part I'm going to start talking about today, is approximations. Okay? And these two things, they tend to work very well in tandem together. You can use them independently, but they often work best together to be able to solve problems that would otherwise be very difficult to solve. So it's again the same theme we're continuing, but along a different line of attack. Okay. So I will continue mentioning randomness in the context of other things, so it's not as if you can forget all about it, but that will not be the primary focus for the next few lectures. The primary focus now will be on how you can think about this notion of approximation. Okay, so let's say you have a particular problem in mind. Right? So you have some problem. It could be, I want to compute the shortest path. I'm on Google Maps and I want to compute a short path from X to Y. Right? Or I'm doing some processing of my search queries. I want to know which the most popular search queries there are. Or I'm doing some kind of split in my data. I'm doing some load balancing. And I want to find the median of a set of numbers because that's going to let me do a kind of a split into evenly sized subsets. And as we know from basic divide and conquer, this is a good thing to do when you're designing something that works efficiently, say in parallel. And just to introduce some terminology here, when I talk about problem, as always, I talk about sort of, find the shortest path from X to Y and G. An instance of a problem, of course, is an actual graph. Right? I mean, so I might have a problem involving graphs, but if I give you an actual graph and say, okay, tell me what to do on this graph, that's an instance of the problem. It's an example of the problem. And so every instance has an actual solution. And we'll call it S. And the solution will have some value. So we're not talking about problems where the answer is yes or no. We're talking about problems where the answer is some number. So in the case of the shortest path, the answer might be the value, the length of the shortest path. In the case of the popular search queries, the answer might be the values of the frequencies of these queries. It might also be the answers themselves, the queries themselves. So the answer might be the query for, I don't know, what's going on. So the query for NFL today might be one of the most popular queries because the NFL season is about to start. So the answer is NFL, but the number is going to be the number of queries that people made regarding the outcome. Okay, so there's going to be a number, which is the value, which is the thing we'll want to approximate, but there's also the thing that leads to it. Right? In the case of a median, again, the median is an entity, but the median has an actual value. Right? All right. So we'll talk about, when we talk about approximations, we'll always be talking about problems that have some value, and you'll see why in a second. And therefore, there is the correct answer to the problem, or the best answer to the problem. If you're doing a minimization or a maximization, then you want the min or the max. If you just want some answer, you want the value of that answer. So there'll be some function v that takes a solution and gives you a number. Say, okay, this is the number for this. But for example, if my problem was finding the shortest paths in a graph, my solution would be a path, and the value of that path would be the length of that path. Right? And then of course there's the best solution, which would be the length of the shortest path. So the S star would be my best possible path from A to B, and v of S star would be the value of that. This is again just some notation so we can talk in a sort of systematic way about these things. So you always have to have these things though. If you have a problem where the output doesn't have a value, again it's like a binary thing where you say yes or no, the notion of approximation doesn't make sense. So you have to have that first. So once you have the notion of a problem that has solutions that have values, and you have some kind of algorithm that's producing solutions, you can now say how good the solution actually is. You might, of course, require that you want to always get the best answer. That's often true for many. The question is, suppose you can't. For almost any problem of interest you're going to be dealing with, the problem is probably intractable. It's hard to, it either seems very hard to solve, or there's some good evidence that it's going to be hard to solve, by NP hardness or something. You're doing some machine learning, you're doing some data mining, you're doing clustering. These are all going to be hard problems to solve exactly. So you're going to want to find some solution that's reasonable. And what we want to know is, how do we formally talk about reasonable? So again, in the world of sort of empirical computer science, you might do things like, well, what might you do? So you're doing some experimental work and you have some solution, you want to argue the solution's a good one. You don't know anything about the theory of approximations. What might you say? How might you try and justify that your solution is good? What would you do? So I'm not asking for a right answer. I'm saying if you've actually done experimental work, you've produced solutions, how do you justify that the solutions you produce are reasonable ones? Yeah.
Produce outcomes by experimenting with my solution and
Yeah.
say like it's probably this much times good, so it should be good.
So how do you say it's good? So you write your paper and you put some tips. So what do you do?
Yeah, so I run it across different data sets, and if it gives good accuracy,
What is good?
results, like most of the times it's correct in assessing this solution.
And how do you check that it's correct? You have some other way of comparing it to something?
Yeah, from some ground truth or something.
Okay, so that's one way. You have some ground truth and you compare and you say, okay, the accuracy is, yes?
Some statistical confidence levels.
So for example?
For an example, if you have some data, you can say that I'm confident the result is true for like 95% confidence.
How would you do that? How would you establish such a claim empirically?
Probably maybe we can model the data in some distribution.
Okay. Is that what you have done in the past? Are you saying you could do that, or you've seen papers that do that, or?
I think that's the common practice.
Sorry?
I think that's the common practice.
Okay, so you model the data in some way and you say, okay, if the data is modeled in this way, then my answers are correct to within some 95% confidence interval. You could actually replace that modeling by something else. How many of you have heard of the bootstrap? It's a statistical technique. Yeah? Anyone? Can I see hands? Yeah, go ahead. Can you tell us about the bootstrap?
Yeah, don't you randomly sample your data?
So, yeah, so why do you do that?
I guess to have a different data set that's built on your same one.
That's right. So you use basically a way of doing random sampling to create what look like different data sets with some statistical guarantees. And that takes the place of a model, because you may not actually always have a model. And then you do your statistical confidence bounds based on that, on the bootstrap. Good. So there are many ways empirically to argue for the quality of the solution you're getting. Some of them can be viewed as semi-rigorous if you assume some data model. They're semi-rigorous because then you transferred your correctness onto the assumption about the model. Some of them are purely empirical, where you do these kinds of sampling tests and you say, okay, this seems like, and these are perfectly, good ways to sort of validate empirical work. The way we're going to talk about here is going to be slightly different. It's going to be more mathematically, more formal, in the sense that we will prove mathematically that you always get a good answer. We won't hope for the best, or we won't try benchmarks, or we won't do statistical assumptions. We will say under no assumptions about the input, in the worst case, you will get a good answer. So it's a very strong claim, because against a worst case claim. Right? But again, like most of these worst case claims, it doesn't always, it's not always as sensitive to fluctuation data, which could give you an even better answer. So it's a pessimistic bond. If it gives you a good answer, then you're happy. It's always as good as that. But it could be even better. Yeah.
Our definition, are heuristics also approximate?
But when I talk about an approximation algorithm in this class, I will mean something that has a provable guarantee of quality and running time. So in my mind, and again, this is a bit idiosyncratic, I view a heuristic as lacking one or both of two things. I tend to call it an approximation. But again, this is just my own way of thinking about this. People often will refer to an approximation algorithm as a heuristic. Ways that commonly show up with quality.
Then why are they approximate?
So you have to essentially reason about what any smart algorithm must be forced to do, and then compare something. So that's where it all gets very interesting and very tricky, and we'll see examples of this as we go along. But just in the way that randomization requires you to change your mindset about how to design an algorithm, Approximation also requires you to change your mindset, because now you're playing a game against an adversary who's behind a curtain and you don't know what game they're playing anymore. All you can do is make general reasoning statements about what they must have to do to be optimal. Okay, and we'll see examples of this. And so it turns out you've already seen an example of an approximation algorithm, even if you haven't realized it yet. So let's take an example of a graph. And we want to solve a problem called max cut. And the max cut problem is, I have a graph and I want to partition the graph into two sets of vertices. So that means you separate them out, one set or the other, such that the number of edges going between the two sets is maximized. I don't care about edges on one side or the other, but I want to maximize edges going between. Does this sound familiar to you?
Problem 5.
Yes, exactly. There's a hidden max cut problem in there. Okay. So let's take an actual example of doing this. Right? So I have this graph here. Okay. And I want to compute the max cut for this. So let me. Copy here. Okay, someone tell me. What I want you to do is color the vertices either black or white in order to maximize the number of edges going between the two sets. So we'll work on the left side. So what do you think? So again, choose some of the vertices to be in one group, and then of course the others will be on the other side, so that there's lots of stuff going between. Not a little, a lot. Yeah?
A and F in one group.
What would be the cost of the cut? The number of edges going outside that set? So one proposal is to put A and F in one side. So then if you look at the edges going out, there's 3 edges coming out from A, and there's 4 edges coming out from F, so the total cost is 7. Can anyone get me a cut that's better than 7, larger than 7? So we have a candidate. We don't know if it's a good one, but we have one candidate. So, so one second, AF gives you 7. So the value of the cut AF is equal to 7. So another proposal is to use D and F. So let's see, so F again had 4. Oh, and D had 4 edges coming out of it, but one of them is to F, so that doesn't count. So D has 3 that are not going to F, also 7. So it's correct. It doesn't improve, but it's also correct.
No, it's 6.
It's 6? Why is that?
F is 3 now.
Because one is D.
Oh, so it's not, okay, good. So that DF cut has now 6 because we have to remove this edge entirely, so we were double counting it. So 1, 2, 3, 4, 5, 6.
So that rules out EDCB, right?
That rules out EDCB as a set.
Yes. I mean, it'll all cancel out.
But EDCB is a complement of AF, so if AF works, EDCB should work as well.
Won't they all keep cancelling each other?
I'm not following. So if you take AF as your cut, you're just looking at edges going out from AF to EDBC.
Yeah.
Those edges still remain the same whether you choose your cut as EDBC or AF. They're complements of each other, right? I'm only looking at edges across them. So that's the complement of AF. So that is the min cut. I mean max cut. Sorry. Anyone else? Any other thoughts? Do we think we are happy at 7? I mean, of course, I'd like to know that 7 is the right answer. And that's hard because max cut is NP hard. You know, to actually solve it, okay, this is a small graph, but if you had a bigger graph, you know, it's a hard problem to figure out the exact optimal solution. So let's say for now, and you can think about this, it seems reasonable to me. So, but we already have, and you've already seen, a point for exactly what I'm proving here. And I'm proving it not because I actually could compute the optimal solution, which is terribly, terribly important. I don't know the optimal solution, but I can get some kind of estimate on it, some crude estimate. The better the estimate I get, the better this bulb will get. But for now, that's all I can do. But that's enough to give me something. And so just like with many things in algorithms, doing approximations is an exercise in creative laziness, right? You want to figure out some way to bound what the optimal solution is doing, but you don't want to work too hard because that problem was hard to begin with. So if you can somehow reason about it in some informal way, you can get a bound that you want. And a lot of the work in approximations boils down to not designing a better algorithm, but designing a better lower bound, designing a better bound for algorithm. And we'll see more examples of this later. Any questions about this? Yes.
So our approximation algorithms, do the bounds have to be deterministic, or they can be randomized, or?
They can be randomized. There's no, yeah, you the same kind of layer of stuff can apply to it.
Basically, to like actually get one half, you have to do like a Monte Carlo.
So this is giving an expected value answer.
Yeah.
So again, you can say with some probability will always be within this. And like I said, you can actually remove the randomization completely from the algorithm. And then you want to, yes.
Well, there's probably ones that you could.
And that's right. And for those who will stay that way. And so we'll say, okay, with some, and in fact we'll see one in a second, with some probability the statement will be like, I guarantee that my algorithm is a C relative approximation with probability at least 9 over 10. So that in other words, what it'll do is that it'll give you an answer with some probability, very high hopefully, it will be the right approximation. With some smaller probability, it'll be crap. Right? And we'll see an example of that. If any of you have taken machine learning or are taking it and have heard of pack learning, any familiarity with pack learning? The word probability approximately correct, that's basically an example of this. So, question, one there, then yes, go ahead.
So, in this case, the algorithm is linear, I guess, in terms of the size of the graph.
The running time?
Yeah.
Yes.
So when we said that we have to have a guarantee on the run, does that have to be like a time bound, or if we say like at most this will take linear time?
I think you should think of this as any algorithm. So it's no different from any other algorithm. I want to know what its running time is, the n squared, n cubed, and for whatever it is, I would like some norm on it. For many problems that we will consider, the actual problem to solve is NP complete. So if you can get any polynomial, that's a good thing. Right? For some problems, I can solve it exactly in n squared. So it's not interesting unless I can do it in much less than that. So depending on the problem that you want to approximate, you will want to design algorithms that have a certain running time or other resource usage, space or time, whatever it happens to be. Right? But you want it to be small. The whole point of doing this is that you're going to sacrifice in quality and you want some big benefit in resources. Otherwise, that's what's the point. Right? If I can save like 1%, if I can get within, a factor 2 of the right answer, but it takes me way too long to do it, it's not worth it. The reason to do this is because it'll speed things up. And this is an example where my max cut at half approximation is linear time. The max cut problem itself is NP hard, and who knows how long it might take. My best solutions might be exponential. So it's a big one. Right? Yes. Daniel, you had a question?
Well, I was just saying I'm familiar with pack learning. It's not important.
Okay. You retracted your comment.
Well, you just said if. Never mind.
We'll get to it, yeah. Yes.
So will this give a bipartite graph with a maximum number of edges?
It will give a bipartite graph with at least E over 2 edges. I'm not saying it's maximum. That would be a guarantee that it's optimal, and I'm not making that claim. That's important. It's an approximation. It's not giving you the exact answer, but it's giving you an answer that's close to the correct answer.
It might not be the exact answer.
It might be. We might get lucky. Good things might happen, but we can't promise that. All I can promise is that we can go within a factor of 2. I cannot promise anything more. And that's the point of these things. I mean, in general, when you implement approximation algorithms of these kinds, they tend to do a lot better in practice. But because you have to give these worst case guarantees, they often have to have a guarantee that looks bad in theory. Right? So it's not one of those things where I overpromise. In fact, I'm underpromising usually. But that's fine. That's the game you play when you do worst case models. Right? You're always there's some input that could cause you trouble. Yes.
Is there typically some level of approximation?
Right. So this statement is not the right statement, right? Well, what would the correct statement be? What is in fact the expected weight of edges between A and B? Zero. So it's half time W plus 0. So the expected total weight of the edges between A and B is thus not the number of edges divided by 2, is the total weight of all the edges divided by 2. Okay, so that number will change. And now you put it here and say, what is this? Well, we know that this number can be at most the total weight of the edges, because the best solution can take all the edges. So now you have half the total weight divided by the total weight. Still half. it doesn't matter. That's the beauty of this method. And that's the beauty of all these things, that often the weights don't matter. That's not always true, but in this example it doesn't. Because the thing, the counterintuitive thing is that you think, oh no, these heavyweight edges, I really need to make sure they're in the cut. But if I pick it random, if I get them, I'll get half their weight anyway. It's not that I only get a teeny bit of the weight, I get the whole thing. And that's where the intuition is different, right? So you're thinking, I want to work hard, I want to find these seven, just pick it random. That's the beauty of randomization also. It allows you to not to worry about some of these details. You could otherwise be very careful, like, oh yeah, take this weight, put it there, do that there. Yeah. Okay? So this works for weighted growth. Okay, let's move on. So is everyone clear on the basic concept of an approximation algorithm and how we reason about it, how we talk about it? So this is the basic template for what we're going to be seeing here. Okay. Okay. All right.
Just one question.
Yeah.
So it's just a randomized algorithm and approximation is
Half.
approximation is in its outcome.
Yes.
Right.
Correct.
So how does randomized algorithm and approximation algorithms different? Because in randomized also we are saying with some probability it's always correct.
But if you're wrong, you could be horribly wrong. So my answer, suppose I don't have an approximation algorithm. My answer could be the exact answer for this problem with probability 2/3. But when it's not, it's much worse.
Okay, so we are keeping bounds on.
Here I'm trying to be more careful. Which is why you can talk about a randomized algorithm, for example, for a problem with a yes-no answer. With some probability I get the correct answer. But if you want to talk about approximations, that's why I mentioned this point, you can't approximate 0 versus 1. If you're not 1, you're 0. There's no ratio there. That's why you have to have an actual value. Okay? So the numerical value actually matters. So so the whole reason we do this is because it's often easier to get an approximation than actually solve the real problem. Sometimes the real problem is intractable, sometimes the real problem is just painful. So, again, and for some problems even n squared is too much, and you want to do better. And one example of what I want to show you is finding the median. Okay? It's a very simple problem. I give you n numbers, and let's write down. So let's call out some numbers. Some numbers between 1 and 50.
5.
5.
20.
E. There's always one of you. There's always one of you. Fine.
43.
Huh?
43.
LN2.
Huh?
LN2.
Oh, it's all smart asses. Two more. 17 and 50. All right. Okay. So we have 1, 2, 3, 4, 5, 6, 7. Good. Nice odd number. Good. Once we have a set of numbers, we can talk about the rank of a number, its position in the sorted order, if we had a sorted order. So for example, the rank, which I've defined here, what is the rank of 5? How many numbers are less than or equal to 5? And now whoever said ln2 has to now actually calculate the value. So what is the rank of 5? How many numbers in this list are less than or equal to 5? 2 or 3? 5, E, and ln2, I think. Yes, ln2. Yeah. Okay. Because ln2 is less than 1. So rank of 5 is equal to 3. Okay. Is there a number whose rank is equal to 4? Well, what's the number just above 5? 17, right? So 17 has 17, 5, E, and log 2. Okay. What 18? What 19? What? Who? Where? There's no 18 in the list. Okay, what's the rank of 50? Okay. So of course the median is the middle of the list. But since we're talking about approximations, I want to have a number as an output. So I'm going to say the median is an element whose rank is, well in this case I should have said n minus 1 over 2, but you get, yeah. So is this here. So in this case the median is 17. And of course, you can find the median in linear time. You don't have to sort. This was one of the cool results in the early 70s. You don't have to actually sort to find the median, you can find the median in linear time by a process of divide and conquer called prudent search or decimation, or kill 1 out of every 10 Roman soldiers in Mexico. That's what decimation means, by the way. But that's what's used to find the median. Okay, so we can find the median in linear time. It doesn't get much better than that. Linear time, what more can you ask for? But of course we will ask for more. I want to find the median in constant time. I don't want to regain. That's just too much work. Who needs the input nowadays? You get the TLDR from a couple of samples, it should be done. Right? Who needs to read the whole thing? Can you find the median in constant time? And that's the question we're going to ask. So let's first define what it means to be approximate. Right? What is an approximate median? Because we're not going to find an exact median. I think it should be very clear to you that if I miss even one element, that could be the median. So if I want to actually find the real median, I'm not going to lose in constant time. Because the minute you don't look at a particular element, the adversary makes sure that was the median element. By putting it very carefully. And there's a formal way to reason this. But can we find an approximate median? And first we define what it means to be an approximate median. We don't actually know what that means. The obvious way to define an approximate median is to find a number n tilde that is very close to the actual median. So its difference from the actual median is small. And we run into big trouble if we do this. So look at that example up there. So the example consists of numbers 1, 2, 3, 4, 5, 6, the number 1000, and the number 2000, 2005. The median of the set is obviously 1000. If you give me any number that is not the exact median, it's going to be really far from the median. Right? Its distance is going to be either 1000 or 994 or something really huge. And of course, I just chose these numbers. I could make them even worse. Right? I could set the small numbers down to minus infinity, the plus numbers up to plus infinity. I can make this difference arbitrarily bad. In other words, what I have shown to you is that finding a median whose value is close to the true median is the same problem as finding the median itself. Because no matter what, suppose you come to me and say, well, I have a 10 additive approximation to finding the value of the median. I say, oh really? Here are my numbers. Find your 10 additive approximation. Like, oh, actually, well, I just found the median itself. Because there's nothing else that even works. You say, well, I actually have 100 approximation. And I give you the same thing, and you see the problem. So what I've constructed is essentially your first hardness of approximation result here. You don't realize that that's what we've done. Giving this example, I've shown you that if you could compute an answer close to the median, you would compute the median itself. And therefore, if computing the median itself takes linear time, there's no way you can do this in less than linear time. It's like the NP hardness reductions, we just computed. So computing an approximate median by approximating the value of the median is hopeless. It's hopeless in that you're not going to be able to do anything any better than computing the actual median itself. So is this point clear? So this point, again, comes up a lot, especially in data problems, where you either can approximate the thing or the value of the thing. And I'm saying approximating the value of the thing is really hard. So let's not do that. Let's change the game. Remember that we defined the median as, in fact, a particular example of a value, the rank function, which is a number. So instead of trying to approximate the median value itself, let's try to approximate the rank, because maybe we want the median because we want to split evenly. And if you want to split evenly, maybe we can split kind of evenly, and then let the Marshall theorem tell us, that's going to be okay. So in that case, can we find an n tilde so that the rank difference number whose rank is similar to the rank of the median? And now our problem goes away because both these numbers, 6 and 2000, are very different in value, but their rank is very close to the rank of the median. So our earlier objection goes away. So see that pivot that we've done here, right? We've gone from saying I want to approximate the value of the median to approximating the value of the rank of the median. And again, when you do approximations, as I said, the first thing you have to do is define what the value output is. So that choice itself will decide what you can and cannot do. And that's a choice you make. Yes?
What about the objection of values is still too far, we are still not approximating well enough?
The question is, what do you want? What is the goal here? If the goal was to get the value, then this is not going to help you. You have to do that. And you'll say, sorry, I can't do that. And you go back and you cry into your coffee and you run a little time out there. But if your goal was to use the median to split, and you're doing load balancing, then what do you care? So it completely depends on the problem. It completely depends on what you want to do with the answer. Whether you want an approximation, what kind of approximation you want, it depends on your problem. All I'm trying to show you is that there are choices you can make. And those choices can have an impact on whether you're able to do this or not. So you have to ask yourself that first question. What do I want this for? Yes?
Do you know if efficient quick sorting implementations use this for the pivot?
Sorry?
Do you know if quick sorting implementations use this for the pivot?
Oh, they completely use this. Because they completely use what we're going to say next.
Okay.
Absolutely. Because it's a waste of time to just compute the median like that. It's too much work. If you do that, then your quicksort would not be very fast. There would be too much overhead for that. It would be still n log n, but the overhead of computing the median would increase your constants by so much that it would not be worth it. And we're going to see how to fix that. So is this sort of setup clear that we've taken the problem, we've defined the notion of value so we can approximate. We discovered our first notion of value doesn't work, and so we've changed it a little bit. Yes?
So what intuition do we have? So right now we've said that, okay, we can approximate the median. But what?
We haven't said that yet. We have defined the goal. I haven't got a solution yet. I've just defined the goal.
Right.
The goal is to do this.
We've defined some metric.
Yes, some metric, right?
But what we still don't have an inkling, is this even possible yet?
Absolutely, we have no idea if this is possible. We just know that that was impossible. We have no idea if this is possible. All we know is that wasn't possible, and the reason that wasn't possible does not make this not possible. In other words, our counterexample to break that argument doesn't break this argument. So it's sort of hanging on for dear life, hoping for the best. Okay? Okay. Let's try to come up with a solution. And here's a solution. Sample an element randomly. That's your median. This is the most brain-dead solution you could come up with. I just pick an element random and say, yay, median. So in this case, for example, I'd like 3. That's my median. That's going to be a random. And of course, this is terrible, right? But how terrible is it? Well, what's the probability we get the exact answer? That's 1 over n, right? The probability you pick the exact answer is 1 over n because only one of those elements is it. Odd, even, whatever. So that's bad. We don't like probabilities to exist of 1 over n. We want probabilities of failure that are 1. But here's the thing, is it close? Can you get an answer can you say that this answer, even though it's horrible, is not too far away from the right answer, under a notion of far? And now let's think more carefully. So think of your input. Now this is where we're going to start reasoning optimal solution, right? If you imagine your input in sorted order, the median would be in the middle. We don't have it, but we can imagine it. So let's imagine the input in sorted order. Let's imagine the median point, and let's imagine a range of size n over 2 elements around it. So n over 4 elements in one. This, of course, by definition, gets you to the element of rank n over 4 and the element of rank 3 n over 4, just by construction. So I'm not measuring in actual geometry distance, just counting in terms of counting number of points. That's what I meant by going that far out. So now we can ask the following question. What is the probability that the random sample you pick is in this middle range, which I'll call the good range, just for no particular reason? So, actually there is a reason, right? The reason I'm calling it the good range is that any element in that range is kind of close to the median in rank. It's not great, but it's close. It's closer than this one. In particular, the distance of the rank is at most n over 4 by construction, because I'm going from rank n over 4 to 3 n over 4. So any element in that set will have a rank difference in the median of at most n over 4. Okay, how many of them are there? There's a ton of them. Half the elements are in that set. So the probability of picking an element, n tilde, at random, that is close, an approximation to the median with n over 4 is at least half. And that's why a random pivot works for quicksort. Because it's a reasonable probability, you get a reasonable split. Because now if I do a split, if I was using this median to do splitting, my recurrence instead of being 2t n over 2 becomes possibly t of n over 4 plus t of 3 n over 4, which is still okay. It's not great, but it's still okay. And it's taken me how much time to do this? 1. I have not read the input. I've done one sample, and I get an answer that's not, that I can actually say something non-trivial about. Much more so than before. Yeah.
Why is it at this happen, not just we have?
I'm being unnecessarily cautious. Yeah, it is exactly. I want to get rid of off by one issues. Yeah.
You're assuming that's sorted, right?
No, I'm not. That's the point. I'm imagining what the world would look like if it were sorted. But when I sample, I don't care if it's sorted. All I know is there is a good region in the middle, and my sample is going to go and pick in the middle. I'm using the sorting merely to reason about the size of my good set. I'm not actually sorting it. And that's where this whole weird twist comes in. I have to imagine the optimal layout without actually computing it. If I have to sort, then I'm done. Set log n. But I don't have to sort. This reasoning works regardless. What I'm saying is, okay, I go pick somewhere, boom. The middle region is where I want to be. That has a certain mass to it. It doesn't matter whether it's sorted or not, but the mass is still the same. Right? So in my example above, let's see, let's go back here. What I'm saying is that the middle region, so let's say, okay, so now n was 7, the median was, so let's say I want to go out to half. So let's say I take the elements, which would be this one, and let's go 1 up, which is 20, and let's go 1 down, which would be 5, and let's go 1 up, which would be 43, and let's go 1 down, which would be E. This set is not sorted, right? But it has 5 elements in my good range, which I've marked there. If I pick uniformly at random, the probability that I pick one of these good elements has nothing to do if it's sorted or not, right? I'm just using the sorting to reason about the quality of that set. Does that make sense? It's a very good question, but I'm glad you asked it, but that's how it works. So. Yes?
So would the cost function always be based on the rank of the number rather than the number?
It depends. Like I said, if you want to do this number, then you're dead.
Yeah.
You can't do anything. Yeah. So it depends on the problem.
Can you do provable better on average by taking more than one but still a constant
Idea 2. Why take 1 when you can take 3? Here's my new algorithm. Take 3 elements. Why 3? Because I want to take the middle one. So we don't want to rest on our laurels. We don't want to be happy with this, somewhat not that great bound that none of you seem very enthusiastic about, even though I am. So we want to do better because I have a demanding audience here. So we'll take 3 elements and take their median. Okay? Now what happens? So again, we have the same quality we want to maintain, this n over 4 to 3 n over 4. And again, I want to reason about the quality of my solution. I mean, the probability of getting a solution. So I've fixed the quality. I want to be within the n over 4 error. So the only question is, can I jack up my probability from half to something much more than half? Right? You can think of this other way around as well. Okay. So now we have to think a little bit more carefully. When do we get a bad answer? So let's think carefully about this. Let's define the regions where bad things can happen. First of all, there's the A region there, which are things on one side, and the C region there, which are things on the other side. The claim we're making, the claim that drives this algorithm's analysis, is the sentence right here. As long as you do not pick 2 elements in A or 2 elements in C, you're fine. So let's think through that. So let's first see if you do pick something there. Suppose you pick 2 elements in A. What's your median going to be? The median of those 3 elements, no matter where the 3rd element is going to be an element in A. Because there are 2 elements in A, one thing is somewhere else, the median is the middle is going to be in A. And that's a bad answer, because that's outside our approximation guarantee. Similarly for 2 in C, it's going to be a bad answer. If you have 3 in C, it's even worse. But if you have only one, at most 1 in A and at most 1 in C, then you could have 1, 1, 1, in which case you're fine. You could have 1, 2, 0, in which case you're fine. Or you could have 0, 2, 1, in which case you're fine. So the crux to analyzing this algorithm is to say what is the probability of a bad event, which is to say what is the bad event, and this is the bad event. 2 or more elements in A, or 2 or more elements in C. If we can somehow make sure that doesn't happen, we'll be okay. And now you can see how we're attacking this problem. We know that the bad event happens when you have lots of stuff on one side or lots of stuff on the other side. But these sides are small. You should be able to get lots of stuff on one side or the other. They're small sets. That's the whole point of them being small. The probability of landing in there is small. Let's do the calculation. What is the probability of picking 2 or 3 elements from A? Well, it has 1/4 of the set in it, right? So the probability of picking 1 element is 1/4. The probability of picking 2 elements is 1/4 squared, and that's it. If you want to pick 3, it's 1/4 cubed. Either of these two things could happen. I'm going to be lazy, so I'm just going to say, okay, let's add these two things. This is double counting, but I don't care. So it's less than equal to that. Similarly, this happens here, you get 5 over 64. So the probability that you do this bad thing is 5 over 32. Therefore, the probability of the good event is 27 over 32, which is now way more than half. Just by going from 1 to 3 and taking the median, you've jacked up your probability of success way higher for that same approximation guarantee. That, of course, I'm waiting for the next question. Yes?
So I guess it makes sense that you want to pick 3 medians, but what do you do with the 3s? Which one do you pick to be your final median?
Oh no, you pick 3, take their median.
Oh, okay.
Their median is your answer.
Okay.
That's why the reasoning is working. Because you're saying take the middle of 3 elements. And that's why if I pick 2 on one side and 1 on the other, then the middle of those 3 has to be that element in the middle. It's going to be a bad element. And that's why I'm going to exclude these 2 cases. That make sense? Yes?
Suppose I take the sample space and divide it by 4, so that I get 4 sample spaces. I find a median of each of those sample spaces.
Wait, so you divide the space, how do you divide the space by 4?
Like say 4.
Sorry?
So like I divide the sample space by
Oh, just 4 groups.
4 groups.
Yeah.
And find a median of all those.
Yes.
And then, try to find the median which is based on these units.
Yes.
Then I can get a probability better than that, like 27 measure.
Sure, you can. You're doing more work.
But it's at least the more better approximation.
Right. There's a trade-off. I mean, obviously you can get the best answer by spending more time, right? If you spend little time, I get the perfect answer. The game is the trade-off. How little work can you do and still get a decent answer? You're going to do a bit more work, you're going to get a better answer. I'm going to do more work, you're going to get a better. You see the trade-off here. You can always jack up one side, then the other side you pay on the other side. Yeah.
And of the 3 medians, you take random element.
No, there are 3 medians. There's 3 elements.
Okay,
that you
3
pick
elements.
at random and take the median.
So you will sort these 3 and then take the median.
No, I pick 3 elements at random. I don't solve anything.
Okay.
Okay, let me. I'm a bit worried now because I think I didn't explain the algorithm correctly. The algorithm is this: pick 3 elements at random. Let's go back to our input. Here, I pick 3 elements at random: 5, 20, and E. I take their median. It's 5. That's my answer. Done. I take 3 time steps to do this. I don't do anything clever. I don't compute medians. I don't divide things up. I just take 3 things. This is constant time, this algorithm. Is that clear? There seems to be some confusion of what exactly the algorithm is doing. I'm not doing anything else. I'm not sorting. I'm not doing anything. I'm just taking 3 elements at random. That's the power of this method. Okay. So back to the analysis. Yes.
I think it should be 1 over 16, not 5 over. Take 3 elements into A. It's equal to the situation, you already can't. You don't need add situation. You take three.
Oh, completely. I was being lazy. I was being very careless. This should really be a.
So actually,
Less than equal.
yeah.
But this is the thing we do, right? I'm trying to upper bound the probability of a bad event. Yeah, you're right. Absolutely right. You have to, one thing I will say though, you must get used to being correctly sloppy. In other words, as long as your inequality is in the right direction, it's okay to be sloppy. Because if you start trying to be very accurate, that's great, but you'll go crazy with some of these calculations, especially in probability. So the trick is to know how to simplify in the right direction. That's what I mean by correctly sloppy. It's okay to simplify by giving a crude upper bound. It's not okay to simplify by giving a lower bound. Because I want to upper bound the probability of a bad thing happening. Yes?
So if we wanted to tighten the bound around M, would that be opposite just by taking a few more elements?
It would. In fact, you can take 5 elements and do this analysis all over again. You could take 7 and do it all over again. And there will be a question about this. Yes. And that's where these tail bones are going to be we've been talking about will come into play. That all these sampling tricks, yeah, as you, again, there will be a trade-off. The more samples you take, the better your bound will get, but it will take more time. Conversely, you can say, well, yes, I know the probability is better for 1/4, 3/4 approximation. If I'm willing to be only half in my probability of error, how narrow does the bound get? So it's the whole confidence. So this goes back to the whole issue of confidence bounds, right? You can give a confidence bound of 95% with certain probability. You can give the confidence bound that's weaker with a larger probability. There's a trade-off between the approximation error and the probability of that happening. This is one point on the trade-off. If I want 1/4 n/4 approximation, I get this probability of success. One more mess that. But this is what I can actually show. That the probability that the rank is less than 0.1 n. Oh, sorry. That's not right. Let me fix that. That the probability that the answer I get is more than 0.1 n away from the true answer is less than half. Which is another pointless trade-off, right? So there's one probability of getting within n/4, which is very high. If I want to say, well, what's the probability I get a lot closer? Of course, the probability goes down, but it still stays. So this result I showed you is actually a trade-off. It's not a single result. It's a whole spectrum of results depending on what probability you want. And the way to prove this is you can say, well, instead of saying n/4, I just move out delta in one direction, delta in the other, write down all my analysis in terms of delta, and then you can get different trade-offs between the probability of error and the actual approximation. So that one result gives you all these things. Okay? Does that answer your question? A little bit? I mean, this is, by the way, without doing anything else to the algorithm. The same algorithm can be viewed as giving you a whole spectrum of behaviors. And if I now throw more points, I can get an even better trade-off. So let's recap, right? So, if you have running time of O of 1, you can pick 3 elements, complete the median. This compares to the exact median, which will be O of n. And again, like I said, the n of approximate median takes only constant time with probability 27 or 32. And like I said, you can do even better and by taking more samples. Okay? All right. Yes?
So are we in approximation algorithm right now? Because
Yes.
Because when we're wrong, we can do all that a lot, right? And that's not something we want.
I see what you mean. Well, yeah, no. Okay, so again, these lines are not as bright as you're making out. I mean, what I'm saying is that when I say I'm designing an approximation algorithm, I want to give an answer that's close to the right answer. Right? That's what I'm doing here. Yes, it also has a randomized element to it. The next one won't. But I'm just giving you this. I mean, the point here is this part. So is this part here. This part is just when you add a randomization layer on top of it. That's separate. They're all approximation algorithms. Some of them have to be randomized, some of them have to be deterministic. But it's like, you can make a little, you can make a little grid if you want, right? So this is randomized, deterministic, exact, approximate. You can, I'm just dealing with everything here. I don't really care whether it's here or here or not. Questions before I move on?
So you're saying that more than half the time you're within 0.1 of the...
Which is a pretty good estimate. And again, if you do more work, by taking more samples, you can get even better. Yeah.
Doesn't that seem like too good to be true? Just 7/32.
Life is good when you have all these tools in your hand. So why do you say it's too good to be true? Are you suspicious? Is there something that you think is... So yeah, so why do you say too good to be true?
Because first of all, the set is not ordered. You get picking elements randomly.
I know it's crazy, right? How on earth could this possibly be true? It's just bizarre. I completely agree with you. It is very bizarre, yet it's true. That's exactly what I want to try to convey. There's a lot of magic here. And it's coming from the fact, let me try to explain this to you. If I want to approximate the median rank, I want you to think about it this way. If I'm saying I want to approximate the rank up to 0.1 n even, okay? I'm saying that there are n over 10 elements, or n over 10 elements on either side, n over 20, n over 5 elements that are acceptable to me, right? Okay, let me say this another way. 1/5 of my data is an acceptable answer. Okay, now does sampling seem more plausible? If a 1/5 fraction of my data is a plausible answer, it seems real. That means the probability of picking something that's good is what? 1/5. Okay, now go back to the homework, right? There's something that can happen which is good, which is probably 1/5. How many times do I need to pick to get something that's good? 5 times. That's the intuition. When you have enough witnesses, when you're trying to find hay in a haystack, it actually is okay. It's not that surprising. But when you have to sort of reprogram to think, okay, what are the set of, how many witnesses are actually candidate possibilities here? And that's why, by the way, approximating the value was so much harder. There was only one witness that got you what you wanted. The median itself. Everything else was terrible. Randomization is not going to help with that. And you can't approximate. There's just not enough structure in the problem. So that's what you're looking for in these problems. There's enough structure, enough witness structure to do it. And then, you don't know ahead of time whether it will. And somehow you have to, often you only realize the structure's there a year after proving the result. But that's what's really going on in these kinds of problems. That's why it's not as incredible or not as too good to be true as it seems on the surface. Because there really is enough witness structure there to find the answer. You just have to say it the right way. But I like that question. It is important to sort of check your intuition and say, okay, this sounds weird. And try to understand why it's weird. And if you still can't get the answer, then maybe something wrong. Okay. Next problem. Estimating large frequencies. Again, if you've taken data mining, you may have heard of this problem. So in our previous example, right, in both examples in fact, we wanted to use approximation to make things run faster. And as I said, that's not always the resource you care about. Sometimes you care about other resources. In this case, we care about space of the resource, not time. It's like with hashing, we want a small space. And so the question is now, can you use the same ideas of approximations to reduce the space of your computation as opposed to reducing the time of your computation? And this again comes up a lot in sketching, when you're doing sketching and streaming and all, you want to reduce the data size down to do something with it. Of course, it helps you in time, but the main thing is it helps you in space. So let's take a problem. I have a stream of m items. Okay, they're drawn from a universe of size n. So let's say n is equal to 10. Give me a stream of items from 1 to 10 that they should have repetitions. Call numbers. Integers from 1 to 10.
1.
7.
3.
Fine, we'll go MATLAB.
5.
1.9 repeated.
Anyone?
10.
Okay. Of course, once you have a set, you can say what is the frequency of an item, right? So the frequency of 1 is equal to 3, the frequency of 7 is equal to 1, the frequency of 10 is equal to 2, and so on, right? And the problem we're asking is, find the top k frequencies. This is a classic problem that's become very important in all kinds of data things. You think of it as an attention focus mechanism. You want to find the most frequent things, the most popular things that you want to pay most attention to, right? The top K, whatever top K means. Right? These could be, again, these frequencies could be coming from many sources. The point is you want to find the top K. So my answer, if K was 2, my answers would be, so if K is 2 here, my answer is going to be what? What are the things that are the top 2 frequencies? It's going to be 1 and 10, or 5 also, maybe 5. So any 2 of these 3, well, 1 and any 2 of these 2 would be fine, right? Okay. Problem clear? It should be, it's trivial to see that if you have n space, you can do this. Just maintain the buckets. Come on. But I don't want to use n space. I want to use much less than n space. And this brings us to a puzzle that many of you have probably heard of already. This is a classic, Google interview question. So pay attention. I give you m items, and I give you a promise. There is one item that appears strictly more than m over 2 times. So it's a majority element. Find it in constant space. So you can't store the input. You have constant. In fact, I'll give you 2 units of space. Find this. How many of you seen this problem before? 1. Oh, yeah, that's good. That's great. That means you can think about it. Okay, I'll give you a few minutes. This is the point of the solution. So again, is the question clear? I give you a bunch of numbers. They're coming by, that's whizzing by like this, right? And I promise you that one. Find it. Yeah? Hey, wait, you know the answer. You said you heard the problem.
No, but just to clarify,
Okay,
on the
good.
screen you can only see one item and then you can never look at it again.
I'm not even saying that. I just said you only have memory to store 2 things. Yeah. But yeah, actually it's also important that, once it's gone, it's gone. Yes. Yes, you're good.
What if you say the frequency is 2 and
Wait, what do you mean the frequency?
it comes 2 times?
Element comes 2 times?
Yeah.
Okay.
And start with that and store that element in the frequency.
Okay, fine.
And each time something comes greater, you start building it.
Some?
Each time you get a new element, and you know the number of times it's coming. Start building it.
Okay, so I get 1. Then I get 1. So okay, I've got 1 as the frequency 2.
Yeah.
Now I get 3. Now what do you do?
Don't update it.
Don't update it, just leave it?
Oh, so you get 1 element each time, is it?
Yeah. Yes.
Pick a number randomly and probability that you are correct is half, more than half.
Yeah, but random.
I don't know why you're all laughing. I'm thinking. You should be thinking too. So pick a number at random. Okay.
Because it appears more than m by 2 times. So the probability that you are correct is greater than.
But you pick any element at random. From which domain?
You're given m items.
Sorry?
You're given m items.
Well, I'm not given the items. I know that they come from a certain domain. So in other words, our domain was 10, right? So you're saying pick an item at random, element from 10. At random from 10? Then what do you do?
But yeah.
Okay, so the algorithm is pick an element at random from the domain. Okay? Since there's a majority element, there's a probability of more than half of picking the right one. That won't work. You see why, right? Okay, yeah.
Yes, so
What if as you're going through the list of items, you count how many times you consecutively see that current item, and if you store the highest number that you see consecutively?
So can you give me an example? So I get 1. My first number is 1.
Right.
My second number is 1.
So if the next number is 1, then your consecutive counter is 2.
Now I see 3.
Then you just store 2 as like a variable.
Then I see 4.
Then you just save it 2. you
And I
go.
see 5.
Well, you go until you get another number that's consecutive more than 2 times.
Yeah, but how do you remember that? You already used up your memory to store this first number.
Well, I mean, you would have basically just 2 variables, one to store the counter and one to store.
Right, so you've already stored your number 1 and the counter 2.
Right.
Now 3 comes in, what do you do? I have 2 units of storage. I have 1 in and I count 2 and I have 3 comes in. Now what do I do?
Well, I guess you need 3. You need the one, you need to keep the previous number.
But I can't keep that, and that's too big.
Well, you still only need a constant amount of them. You only need the current number and the number you've seen before that and how many.
Okay, so suppose my numbers are 10, 9, 8, 7, 6, 5, 5, 5, 5, 5, 5, 5, 5, 5. Now you have to store everything before to get to the 5, 5, 5, 5, 5.
No, you wouldn't, because like so when you go 10 to 9 to 8, you wouldn't need to remember 10 because you know that it wasn't consecutive.
Suppose I got 10, 10, 9, 9, 8, 8, now what?
And then any of those.
But what does your algorithm do?
Well, I mean, it would just remember the first time something was repeated.
So, okay, so I give you 10, 10.
Right, and so.
Okay, you got 10. Now I give you 9. What do you do?
You'd just be storing it, if it's a bad algorithm.
No, it's not a bad algorithm. What I want you to do is not play cat and mouse with my counter examples. I want you to give me the algorithm. I'm trying to force you to define your algorithm fixed without changing it as I give you inputs.
Right, okay, so you need to store the number you're currently on, how many times you've seen that in this consecutive. You need to store the number that you've seen the most and how many times you've seen that number.
But the most, that's the problem. How do you see the most? You can't do that. You don't have enough.
I've seen the most so far.
But that's so far is the same as everything, right? I mean, that means that by the end of the run, the number you've seen so far the most is in fact the most frequent item. You don't have a way of doing that. We don't have enough information to store the number we most frequently see.
I mean seen the most consecutively, not the most iteratively.
Right, but if I have a whole...
Is the number that is consecutive the most is more likely to be the number that occurs most in the list.
Yeah, but this 10, 10, 9, 9, 8 example is going to confuse your algorithm because I might slip in 10, 10, 9, 9, 8, 8, then 10, 10, 9, 9, 8, 8, and 10, 10, 10, 10, 10, 10,
I'm not
10,
saying
10.
it'll always be correct, that's not the point.
Oh, but that is the point. I want to be correct.
But we're still talking about approximations.
We are, but they want to be correct. In this case, in this particular problem, I want to give me that answer. But no, but I think you're on the right track here. This is a good, so those of you who are too busy talking and not listening, his idea of what is going to be the solution. I'm just trying to sort of flesh it out a little bit more, see where it's coming up. So I don't even know which order, so we'll start here.
I don't know if this counts as cheating because I saw something similar in data mining class.
That is cheating. yeah, you got a hand up here.
Can I just pick 2 numbers at the same time? If these 2 numbers same, we just use this number. If these 2 numbers are not same, we just pick it again until we got same number. So we regard it as that way.
So suspiciously like my next slide, but we'll get to that.
Really?
Yeah. Any other hands up? Yeah.
We store min and max. We store min and max, and we select randomly from that defined parameter.
How do you get the min and max?
So,
You compute the min and max.
yes.
And you pick one of them at random.
Yeah, so we have 2 storages. One you.
Okay, so my input is 1, 5, 5, 5, 5, 5, 5, 5, 5, 5, 10.
Yeah,
So your answer will be 1 or 10.
Yeah, so you pick a number randomly from between 1 and 10. So
Oh, randomly between 1 and 10?
Yes.
But that's just like the original one, just
yeah.
pick it random.
So it's just the domain is defined now.
But I gave you the domain, it's 1 through n.
Okay.
Okay, yes.
So does this guy have passages?
No.
Okay, so I have an idea. How about we bubble sort it with...
You can't, you only have 2 units of storage.
I know, but so the way I do this is I start at the beginning, I swap the 2 elements.
Then
and I swap
no, you're gone, that's gone. You can't write down. You only have 2 units of storage.
I only have 2 units of storage.
Completely, no, you don't even have the input. You don't have the inputs at all. You can't read the input either, it's gone.
So I only have 2 units of input, and I can only read the input once.
Yeah.
Okay, that's different then.
Exactly. Yeah, follow.
Is there a value?
Nope.
So I would just, first one, only then the second one
You can't, you read it's gone. No, you can't. That's what I'm, okay. Yes, one last question and we'll move on. Yeah.
So in the 2 units of storage, in one of the units, I just
Everyone, please.
the number of times a particular item is being stored, and I have a promise that it appears more than M5.
But which one do you keep track of?
So the first
It is 1, 2, 3, 5, 5, 5, 5, 5, 5, 5, 5, 5.
okay, so I have one in there,
Yeah.
and then I keep counting the next two.
But I don't see 1 again. Its count is going to stay 1. I have to have a way to switch, to change my mind. Okay, so think of it this way, and you probably can come up with a solution yourself in any one of different ways. But here's a way so after many years of knowing this algorithm and the solution, I had to come up with a different way of proving it for other reasons. And so there's a different proof altogether, which is kind of, I don't know, I think it's interesting. So think of it this way. Look at your sequence, right? I promise there's a majority, right? So if there's no majority element in the first part of the sequence, there must be a majority element in the second part of the sequence. Right? So, in other words, if everything balanced out nicely in the first part, so the majority element didn't show up, then all of its extra frequency has to show up at the end. So it must be the majority element there. Right? Because it occurs more than half the time. So if it's less than half here, it has to be more than half there. Okay? Just keep that in mind. So if I have a sequence and I know that sigma is a majority element and sigma 1 does it, then sigma 2 must have a majority element. And the key point here is that, and this is something that a couple of you were alluding to, the first sigma 1 can be of length 2. This is true for any sigma 1. So I think you were both talking the same thing. Imagine I have just 2 elements in the first set. If I take 2 element sequence, can I tell if it's a majority or not? Well, if it's the same element occurring twice, then yes, it's a majority. If it's not, then it isn't. Right? Yes? Okay. I just said if sigma 1 doesn't have a majority, then sigma 2 must have the majority element. So if I read 2 elements and they're different, it doesn't have a majority element, I can ignore it completely. Just throw it away. So if I take the first element, take the second, and they're different, act as if they were never there. They cannot be part of my answer. Okay? Because if it doesn't have this thing, if they're different, they don't form majority, and I just argue that it'll show up later on. So, in other words, if my majority element was 1, and my first two elements are 1 and 5, I can throw them both out. 1 will show up later. If the majority element was 1, the 2 elements are 5 and 6, I really don't care. But either way, it doesn't matter. If the 2 elements are the same, then maybe this is a majority, and we should keep its count. So in the case you're saying, you see 10, 10, keep the 10 and keep its count. That's exactly right. You should do that. But what do you do next? That's the key. Okay. So now you know you have 2 elements that are the same. What would make that sequence no longer be majority? If I saw 2 more things that were not that. Right? Well, how do I keep track? Well, I see the next element. If it's not that, I subtract it. So I saw 10 2 times. The third element comes in, it's not 10. So now my score is 2 to 1. So I reduce it. 1 extra over majority. If I see a new element that's not 10, it's going to go down to 0. And then I can ignore this whole sequence. And start all over again. So this is the algorithm. You have 2 storage, you have the storage for the item itself and the storage for its count. You read the first element. If it's whatever it is, you increment it. If it matches what you have, you increment the count. If it doesn't match it, you increment the count. If the count goes to 0, reset and start all over again. That's what this last step is. And return the element. That's it. You are guaranteed to find the majority element. Yes?
So this isn't constant space because your count uses logarithmic bits?
Oh, yes, log bits. But apart from that, log words of the input. I mean, it's constant number of words of the input. You must be a complexity theorist. Because the only people who care about that. So yes, but yeah, words of the input, yeah. Now there is a proof, and this is the proof here. I don't know if the proof is as interesting as the reasoning that I was just giving you. But this is a proof. Namely, if you do return some item, okay, and it has some true frequency, right? It's going to return some number in the counter which is less than its true frequency. Because I count it, but I also decrement things. So the value I return for the frequency of this item is never more than its true frequency. It's always less. But how much? It turns out its reported frequency is at least this minus some. It's at least close to this. So the difference, here's the approximation. The difference between this and the true value is not very large. Why? Think of what's happening. Every other element is going to try and reduce this element's frequency, the one that I returned. It had frequency Fi. I don't know what it is, but imagine I have this Fi again. Every other element is going to try and decrement that count by the second step. So the number of decrements it could possibly receive is as much as n minus its frequency. So its actual frequency reported will be its original frequency minus all the decrements, which is 2Fi minus n. But we said Fi was more than n over 2. So there's going to be this element, if it was a majority element, with our frequency more than 1, everything else with our frequency of 0. So since I reported it back, it had a frequency of at least 1, which means it had to satisfy this property, which means it was an element that had a frequency more than n over 2. I just told you there was exactly one of those. There has to be exactly one of those. That's your answer. So again, the proof is a little bit twisted. But the basic idea is that you can forget an initial prefix where you don't have a majority, and that's keeping track of that by doing that forgetting. And the last thing I want to say before we go is, this is the formal guarantee. That the error of the approximation is at most n over 2. It's a terrible approximation, but it's enough for the majority argument. And next time, we'll talk about doing much better than this. Okay? So sorry I ran over a little bit, but we'll continue. Yes?